Last time we added error handling to our language via the unconditional aborts and the throw and try catch functionality. Today what we're going to see is that those features are actually special cases of a more powerful underlying feature. This underlying feature is called a first class continuation. And I think that this is an unintuitive feature, so we're going to define it relatively fast. And then once we define the feature, then we'll spend quite a bit of time exploring how it works and what it can do. So the way that this feature works is that there's a new form inside of E that is called call CC. And you can treat it like a primitive. When we have a context that reaches a call CC, what we're going to do is we're going to call the function v. We're going to treat v as if it's a function, and we're going to give it one argument. And this argument is going to be a function itself that takes one argument, x. And what it's going to do is it's going to call abort. Right? It's going to call abort on taking the context E and filling it with x. Now this is really strange because what it means is that whatever was going on outside of the call CC gets copied a second time. So let's look at a little example program. Imagine we have +1, and then we have call CC, lambda k, then we have +2 k3. Okay? So let's walk through what happens in this program. So the first thing that happens is that we're going to evaluate this call CC because that is in the redx position. So in this case, E is equal to +1 and then the whole. Okay? So that means we're going to get +1, and then we have this v, which is that lambda right there, +2 k3. Okay? And we're going to call that function with this lambda right here, lambda x, abort. Then we take the E context right there, and we write +1x. Okay? So that is the very next step. Now this function right here gets substituted for k. So we're going to end up with +1, +2, then we're going to have lambda x, abort, +1x, close that parenthesis, and then we're applying this to 3. All right? Now the next redx is applying this 3. So we're going to take that 3 and substitute it in. So we're going to get +1, +2, and then we're going to get abort of +1, 3. Close the abort, close the plus, close the plus. Now we're going to reduce that to 4. So we get +1, +2, and then we have abort 4. Actually, sorry, abort is not a evaluation context. Okay, so then this evaluates to +1, 3, which then evaluates to 4. So what goes on right here is that call CC has effectively allowed us to skip over this +2 and make it so it no longer happens. Inside of this code, we have the opportunity to observe what the context around it was going to be and call it in the future. So we observe the context at this point and then save it and then reuse it later. There's a lot of features that we can build with this feature. let's look at an example. So the first thing that we're going to do is we're going to establish a little abbreviation. We're going to say that let CC K E is going to be the same as call CC lambda Ke. That's just a convenience. All right, so now that program that we wrote before would be +1 let CC K +2 K3. That's much cleaner. Okay. So what are some example things that we can do with this? Well, in many programming languages, functions have the opportunity to return early. So for instance, in C, I can write a function like this. I can write int f of int x, and then I could write if x is less than 0, I could return -1, then I could say if x is equal to 3, then I could return 0, and then otherwise I could return x times 2. Okay, so that's just a little function that I could write. Now, this function would be a little bit obnoxious to write in our language without call CC. So in our language, we would have to write something like this. We'd have to say lambda x, then we'd have to say if x is less than 0, -1, and then in the else case, we would say if x is equal to 3, 0, and then otherwise do x times 2. Okay, now notice that we have to have this indentation because we have to have the each part inside of another one. It's not possible to end something early. Well, returns allow us to do that, and we can put that inside of our language in the following way. So we could write the following. We could write lambda x let CC return, and then we could write when x is less than 0, return -1, when x is equal to 3, return 0, and then otherwise just have multiply x2. And now that is a valid program. So let me just put in the rest of the parentheses. Okay? So a let CC allows us to define return ourselves. And naturally, what should you be thinking? You should be thinking, aha, I can put this in the desugarer. I can make it so that my desugar function says that whenever I see a lambda with a function name and some variables in a body, I'm going to turn that into let CC, sorry, I'm going to turn that into a lambda with the function, the variables, and then I'm going to stick in a let CC with the word return, and then I'm going to call desugar on the body. Okay, so you can make it so that now once we have let CC in our language and call CC, we can just make it so our functions always have returns. We don't have to explicitly implement that feature separately. Similarly, we can make it so that our language supports break and continue inside of while loops. So recall the definition of a while loop, where we had while C E. It was equal to a function called rec with no arguments. And what it did is it says when C, do E, and then call rec recursively. And then we call that function right away. Well, we can add break and continue in the following way. We can say that we're going to still call the function, still have rec with no arguments, but what we'll do is we'll do let CC break, and then we'll have when C, and on the inside we'll do let CC continue, continue, and then we'll have the body expression. That's the body expression EB. And then after that, then we'll call the recursive function. And then we'll close the when, close the let cc, close the function, and close the function call. So now what happens is, during the evaluation of the when, if the body calls continue, it skips to the end of the body and does the recursive call. And if it calls break, it jumps outside of it and then returns. Return, break, and continue are all examples of, so return, break, and continue are all examples of control constructs. They allow you to change the control locations in the program. And call CC is an example of first-class control. There's this concept in programming languages called first-classness, which basically says, like, is some feature something that only the only the language designer has access to, or is it something that is treated equally with all other concepts in the language? So for instance, in a language, it's pretty typical for there to be first-class numbers, where you can write down any number you want. But some languages like Pascal and C, they don't have first-class functions because they don't have the ability for you to write down a function inside of any position in the program. Functions can only appear in special top-level positions. But when we added lambdas, that gave us first-class functions, the ability to have functions anywhere in the program. So what call CC does is it gives us first-class control. We can have control constructs in any place. Now, how can we implement this inside of our CEK machine? We can implement it in our CEK machine, and this will be, we're turning our CEK4 machine into CEK6. What we're going to do is we're going to add a new kind of value, and it's called the continuation value. So it is a value that wraps a continuation object. And then continuations are going to have one more thing, which is called a K call CC. And it embeds a K object. And here's how it works. When you do a call CC of E, we then have an environment and a continuation K. What we do, do we need that? Okay, I think it'd actually be more beautiful to not have this thing right here. We just have a new continuation object. So when we do a call CC of E with an environment and a K, what we're going to do is we're going to we're going to generate a call. Yeah, okay, this is why I didn't do that. Sorry. I wonder if I can do an undo. What does that do? Aha, there we go. All right, okay. So what this is going to do is it's going to focus on the E and give us a K call CC continuation. All right, next, when we have reduced that to a value, so we have some value, an environment we don't care about, and a K call CC, what we're going to do there is we are going to generate a function call. We're going to generate a function call where we're going to have the continuation object that has that continuation K with no environment, and we're going to have a K app where we're going to apply this V right here with an environment we don't care about, no other arguments, and K. Notice that K here gets duplicated. There's the K inside there, and then we've duplicated into this continuation value and into that component. Then later on, if this value is ever called, so imagine we have a function, a value, where we have an application where we're trying to call a continuation value, k. There's an environment we don't care about, no other arguments, and then k prime. Actually, let's call this k prime, and we'll call that k. Then in that case, what we're going to do is we're going to take this value right here, and we're going to return it to the embedded k prime. So essentially what we're going to do is we're going to throw away that k. That's what the abort does in the normal implementation. It throws away that and instead switches to returning to k prime. Let's walk through an example of this running. Let's walk through the little example. So we're going to have +1 call cc lambda k +2 k3. Close that, close that, close that, close that. All right. The initial environment is going to be empty, and the initial continuation is going to be kret. The first thing that's going to happen is that we're going to get down to remembering the call, to seeing the call cc. So we'll get down to call cc with this thing right here. Let's just label that real fast. Let's label that program A. So call cc A. The environment is still empty, and the continuation says we have a k app of +1. There's an empty environment. There's no other arguments, and there's a kret inside there. Okay, so now we're going to go focus on A, and we're going to have a k call cc, and we're going to have this thing right here. Let's label that k1. So we're going to have k1 as the continuation. Now we're going to evaluate A, and it will turn into a value. It will turn into a closure with the A code and nothing saved. The environment's empty. We have k call cc k1. All right, so what happens next? So then we're actually going to call that, and we're going to call it with a continuation object. And that call is going to result in the code +2 k3 running, where the environment says that k is bound to a continuation object that stores k1. And the continuation is k1. Then what we're going to do is we're going to get down to calling k3, where the environment is the same. I'm just going to put quotes there. And now the continuation says that we have an application where we have +2, no environment, no other arguments, and then k1. All right. So then we're going to look up k and get to 3. So we're going to have 3, the environment's the same, and we're going to have an application where we have the continuation k1, which we looked up from k, an empty environment, no other arguments, and then after that we're going to have k app +2, empty environment, that, and k1. Okay, so notice that k1 appears in 2 places here. It's a value inside there, the function we're going to call, and it's in that slot. But now this 3 is going to be called there. So what happens in the rule? Look back. This is the rule. We see that k there, and that means we're going to go to it. So we're going to go that 3 is going to go to k1. So we're going to throw away this app continuation and that app continuation and just go to k1. And remember what k1 is a k app of +1 null empty kret, which then that means that we're going to get +1, 3, so we're going to get 4 null in kret, and then the answer's going to be 4. Okay? Now, something that's really remarkable about continuations is it turns out that the continuations also allow us to implement try and catch ourselves. So this is pretty remarkable. Here's how it's going to work. We're going to define a global variable that's going to be called last handler. And last handler is going to be a box that's going to contain inside of it a function that takes an exception value, and it will call abort on that exception value. All right. Then we're going to write the function throw. And throw takes in a value. Then what it does is it's going to unbox last handler and then call it with v. So if there's no catch handler, then what throw is going to do is it's going to call abort. But here's the special thing. We're going to change our desugarer so that when it gets try eBody with catch eCatch handler, it's going to turn that into a function that we're going to write that's called TriCatch star, and it will give it EB and EC. Now, how does TriCatch star work? TriCatch star has the following implementation. It takes as an argument the body and a new handler. All right. The first thing that it does is it remembers what the old handler was. So it says let old h, that's for old handler, equal unbox of the new handler. Okay, so that's step one. Then what we're going to do is we're going to do let cc, and we're going to call this here, so we can come back here. Then what we're going to do is we're going to set box the last handler to a new function. This new function is going to take an exception argument, and then what it's going to do is it's going to set the last handler, set box, the last, let me fix that. I always forget that I can erase things, and I just kind of scribble a lot. So we're going to set box the last handler to be the old handler, and then we're going to call here and give it as an argument the result of calling the new handler on the exception value. Then what we're going to do is we're going to do begin zero of the body, which we're going to call as a function. Oh yeah, I forgot to do that. This right here, yeah, let's go back. This should have been a lambda that takes no arguments, and then the body, and then EC. Okay. Then we're going to call the body, and remember what begin zero does is it evaluates this, returns the answer, and then evaluates the effects. And the effects are going to be set box of the last handler to the old handler. And we close that one, close that one, close the lambda. Okay. So the idea here is that every time you do try catch, you modify this global variable, the last handler, and by modifying that global variable, you are identifying the continuation, the code that you need to skip over, right? Because throw was called at some point inside of this body, and there was some continuation there, but we're going to skip over that and go back to this spot where the try block was, evaluate the new handler, and then keep going. So the thing that's remarkable about this is that now our language doesn't need to know what try and catch are. They can actually be implemented inside of our desugarer. So what I recommend that you do is you go to your CEK machine and you get rid of the handling of try and throw, and you just put them inside of your standard library like this. Okay, there's another form of code, sorry, another control feature that's really pleasant to implement with continuations. And it is called a generator. The idea of a generator is it's a function that when you call it the first time, it does one thing, and you call it the second time, it does another thing. So let's look at an example generator. So I could say let f equal make generator. Okay. And make generator is going to take a function that takes one argument that's called yield. And then we could call yield on 0, and then yield on 2, and then yield on 4, and then we'd be done. And we'll do this inside of plus f. Now this program is going to return 2. Because the first time we call f, it returns 0. The next time we call it, it returns 2. And if we ever called it again, it would return 4. Here's another example generator. Let evens be make generator. Okay. Lambda yield. Then we'll say let I, actually, let's do it like this. Then what we'll do is we'll define a recursive function that takes as an argument I. And what it does is it's going to yield I, and then it's going to call itself recursively with 2 more than I. And then we'll start off by calling it with 0. Here, when we call evens the first time, it's going to return 0. Then when we call it again, it's going to return 2. If we call it again, it's going to return 4, and so on. It'll never finish like it. It'll always have more even values to return. If we call it again, it'll give us 6. So this function right here represents an infinite stream of numbers that are computed by this algorithm. So this is what make generator does. There are languages that support this, such as JavaScript and Python. They both have generators as a feature that's built into their compilers. But what we can do is we can write make generator as just a program in our language. Here's how it works. So make generator of f, so is a function that takes in f, and what it does is it's going to say let f in progress is going to be an in left of false. Then what we're going to do is we're going to return a function. This is the function that will actually be called. And then what it's going to do is it's going to do let cc, and we're going to call this local. And what we're going to do is we're going to do a case on unboxing. Ooh, sorry, I forgot. This is going to be in a box. So let me adjust that. So this is in a box. Okay, so we're going to box that. So we're going to do an unbox, of f in progress of, now if we got an in left, then that means that this is the first time that it's called. So if it's the first time that it's called, what we're going to do is we're going to define a new variable that's called current, and it is going to be a box that has local inside of it. And then we're going to call f, that's the function that we were given, and we're going to give it yield. And this is our implementation of yield. It's a function that takes an answer, and here's what it does. It's going to do setBox of current, so it's going to modify current, and it's going to modify current with the result of calling letCC next, and then we're going to do setBox of f in progress to an in right of next. So we're going to close that, close the set box. So now what we're doing is we're saving this particular call location for the next time it's called. Then what we're going to do is we are going to unbox the current. This is before the result of calling this, and send it the answer. Close that parenthesis, close the let, close the set box, close the lambda, close the f. And then what if we got an in R? Then the in R is we're gonna call the thing inside of it the resume. And so what we're gonna do is we're gonna call resume with local. So how does this work? How it work? Oh yeah, and then we gotta close the case, close the let, close the lambda, close the final lambda up here. Okay, so this is the whole implementation of make generator. What happens is the function, the user function, comes in right here, and then we return this lambda. We remember the time that the user called us. We're going to call that local. And if we've never been called before, we're going to run this code. This is the main code that's going to happen. It's going to have a local variable called current, which is going to keep track of where the return is supposed to go, which is of course going to start off as local. It's then going to call the user-supplied function f. And it's going to get, and then yield is going to be called at some point with an answer. We're going to remember when yield was called, and we're going to call that next. We're going to remember next so that we can go back to that same call location, and we're going to give the answer that was provided to yield, to whatever the current handler was, which in this case is the local one. But then if it gets called again, then that means that we have a resume here. So then we're going to call resume, and we're going to give it the new local value, which is going to get returned to this parenthesis right here, which means it's going to get set to current. And then we're going to go back inside of f, and if yield gets called again, well now current is this local thing that went through there. So basically what we're doing is it's like, here's an analogy. What make generator does is right now in the present, you make a wormhole to the future. And then you wait for the future to send you a message, you prepare your answer, and then you send it back through the wormhole. Current is the wormhole, and when we send local in, that's us sending where we want the answer to go through the wormhole. It's very beautiful, and it allows us to have a very succinct, efficient implementation of this generator feature. Now, let's go back and talk a little bit about the CEK machine implementation. We have this rule, so we have these new kinds of values, these continuations. And we have this new rule that says when we get a value and we're sending it to call CCK, we generate a continuation object with an application to that value. Let me just put that as null. With an application to that value. Now what's really going on here, this k value right here is being copied twice, or at least there's a reference to it. So this is really bizarre, because recall that the continuation objects, they are implemented in most languages as stacks. And what's special about a stack is that it has a static memory management policy. You always know that when you push something onto it, that's when you allocate. When you pop something off, you're totally done. But now we have two references to it, which means that there are potentially aliases. So we can no longer necessarily free them whenever we want to. Sometimes they may already exist. So how does this work in practice? In practice, if you have a language that's implemented like a CEK machine, then you're basically allocating your continuations in the heap, and you're not using the computer's stack features. If you are going to allocate your continuations on the stack, then what you need to do is you need to, at this point, make a copy of the stack into a new location. That can be expensive, and it can make it so that it's expensive to call continuations. There are many languages that do this. They optimize normal call cycles, and then they make it so that when you do a continuation capture, that's expensive. There's another strategy where what you do is inside of the stack frames, you have a little pointer to where a copy of this stack frame is somewhere else on the heap. And if you ever need to do a continuation capture like this, what you do is you flag the continuation by saying, I needed to make a copy of you. And then if it ever gets popped off later, then rather than popping it off directly, what you do is you make a copy of it and you store the location in the particular location, and then you pop it. So that way, you are sort of lazily copying it. That's what Racket does, and that's a pretty common implementation technique for continuations in high-performance languages. There's another strategy for implementing continuations, and this is pretty exciting. Basically what it does is it allows us to transform a J10 program, that's the language with continuations, into a J8 program. That's the language. So this has call CC, and this one has no call CC. And the way that it works is basically every function over here, say imagine we have a function that takes f and x. So if the function's name is f and it takes x. We're going to transform that into a new function that takes an additional argument that we're going to call k, and that is the continuation. And so if this function before used to say something like it's going to return x plus 1, this new function is going to call k and it's going to give it x plus 1. What we're doing is we are explicitly representing the control flow of the program. This is called CPS, or continuation passing style. And continuation passing style modifies every function in this way to always say that there is this additional continuation argument. And then we can implement call CC in the language itself like this. So it takes in a value and a continuation, and then it just calls the value with the continuation and sends that through. Sorry, made a mistake. It's going to call the value, and it's going to give it the continuation, and it's going to give it the continuation as its continuation, because V is, of course, going to take this thing and send it the answer. So basically, now that's where the copy comes from. Continuation passing style effectively makes it so that your compiler doesn't need to know about continuations, only your desugarer does. And then it makes it so that all control flow is also heap allocated. So my personal advice is to not implement it this way if you're using a CEK machine, but it might be a strategy for writing a compiler for a language like J10 to a language like C. So that's where continuation passing style tends to be used. All right, that's enough for today. And next time we will look at more things that can be done with continuations.